And now I want to know if you've understand everything that I said. So as example, can someone please calculate the derivative of x in cubic power from you? So, yep, it's correct, great, you've calculated the derivative, and actually he used the notion as the x. This is called differential of function, and basically it's just the same as delta x. It just defined as delta x. So the differential of x is equal to delta x. It's just the same. So now let's see some tendencies for this power function. So if we have x in power of 1, this is equal to 1 in power in 1. X in power 2 is equal to 2x actually in power 1, can be written. And actually we can write as 1 multiplied by 1, and 1 is equal to x in power of 0. So you can see that 1, 1, 2, 2, 3, 3, and 0, 1, 2. So actually you can prove mathematically, but we will just write down that derivative of power function is equal to n multiplied by x in power of n minus 1. So if we want to calculate derivative of power function, we just take our power here and reduce our power by 1. And the last important function to calculate is exponent. So we've talked about this function before, and graph of this function looks like this. So it's just to remind that it's always bigger than 1, than 0, and it's pretty much always increasing in that way. So it can be calculated as Now we can, using because this power we can write down like that. Now we can and it's again can be mathematically proven that this fraction is tends to 1 as delta x is getting smaller and smaller. And actually this is the reason why we've talked about exponent and why this number, Euler number, is so important, because this fraction actually is 1, and that means that derivative of exponent is equal to exponent. So all these derivatives are obviously written in Jupyter Notebook, so you can review them later, and I recommend you to remember them, because we will use these functions and their derivatives very, very commonly in this course. And then these functions can be remembered, but we don't want to calculate derivative of function which differs from that. Like, take a look at 5 multiplied by x squared. We don't want to do all over the same result, and we can actually do this and so we can see that 5 is a common denominator, and we've already proven this fraction is equal to 2x, and that means the derivative of this function is 10x. And we don't want to do this for all functions if they can be derived from these simple functions, like if we have some function f of x and it can be represented in this way, then we have special rules of differentiation that I'll write down for you. So, first of all, as you've already seen, if we have some constant and multiplied by function, then derivative of this whole function is equal to constant multiplied by derivative. Then, if we have two functions, what to do with them? So we can see that derivative of this function can be represented as it can be represented by definition but then we can set these two functions apart and get two fractions. And what this fraction represents? What do you think?
The derivative of sum of the functions equal to sum of derivative of each of functions.
Correct. So each of this function is, each of this fraction is a derivative of f at x of g of x, and that means that we can write this rule. And obviously it holds for subtractions, so you can prove this. And finally, we have three more rules, which I'll just write down and without proof, because proving them it's quite hard without knowing all mathematical background and all theorems. So I'll write down that multiplication rule. So derivative of multiplication of two functions is equal to derivative of first function multiplied by second function plus first function multiplied by derivative of second function. Right? So for example, x squared can be represented as x multiplied by x. And if we take derivative by this rule, so a derivative of x is equal to 1 multiplied by just function, second function, or x. And now plus first function, x, multiplied by derivative of the second function. Well, derivative of x is equal to 1. So we get our 2x, which corresponds to this rule. So we can actually prove this rule by using this multiplication differentiation rule. Also, there exists quotient rule. So this is derivative of x multiplied by second function minus second function, first function multiplied by derivative of second function. And it's all divided by square of the second function. Again, we can take a look at simple examples like x squared. Or for example, let's calculate derivative of a function one divided by x. Derivative of this function can be calculated in two ways. First way, we can represent this function as x in power of -1 and then use this power rule for derivatives. So we can get that n is equal to -1. This is our n. And just by rule, we can get that, or it can be rewritten as following. So we've just used the rule. Now we can use first rule of differentiation to calculate the same derivative. So in this case, our first function is just 1. Our second function is x. Right? So first of all, we find a derivative of 1. It's constant. So 1 is a constant. That means that its derivative is 0 multiplied by x, by second function, minus first function, 1, multiplied by derivative of second function, 1, and divided by second function in square, x squared. So as you can see, the derivative is the same, so that means that everything works fine. And final, probably the most important and the most powerful rule we will use. What will happen if we will try to find derivative of function inside a function? So what that means? Some functions are, you just cannot represent them with these functions. For example, exponent in power of x2. So this can be rewritten as, right? But that function is not the same, so it's even more complicated. And we just cannot represent this function in terms of this. That's why we will use two functions to represent this one. So we can write that f, and it depends on g, and g depends on x. So we can introduce these two functions, and this function will be just x squared. And this function will be exponent from g. So how does it can be also used in life? For example, you want to calculate this function on your calculator. In that case, you just took your x, you square it, so you get value of this function, and then you took value of this function into your calculator, and your output will be the real value of this function. So the same way as you do in calculator in real life, the same way you can do in math, and you can represent some complex functions as composition of two more simpler ones. So derivative of such function will be derivative of first function multiplied by derivative of second function. And in first case, we took derivative by g, and in second case, we took derivative by x. So in that case, our main variable is g, and in that case is x, our argument of function. And let's take a look how it works on the same example. So derivative of this function is equal. It's equal to derivative of this function by g. This is our function. And if we take derivative of it by g, then we will get, by this formula, we will get e to the power g. Also, we will need to take derivative of this function by x, and in that case it's equal to 2x. Right. So now we multiply both these derivatives by the rule e to the power g multiplied by 2x. And now, because we want to have function which depends only on two arguments, we want only one argument, x. That in that case, we just substitute our g, which is equal to x squared, into this expression, and we will just get 2x multiplied by so that's how we use fifth rule, and it's quite important because we can prove some. We can use these rules in cooperation with this to calculate any derivative you want of any function which can be represented by elementary operations like subtraction, multiplication, and others. That's all about our derivatives. And have you written all the rules? Yes? Okay. So derivatives will be used, and they will be used quite soon. But right now, the most you need from them is to practice. So that's why in homework you'll have to calculate some not very simple actually functions, which can be calculated using these rules for the most basic functions, and also this fifth differentiation rules. And the more you need is to just practice, to be good at it, because basically differentiation is the same as algebra, as for example, like simplifying some polynomials. You just need to be practicing every time. And finally, now we are talking about optimization. So finally we can start machine learning course, because everything that was before it was just preparation. So we can write it. Optimization is so let's before giving a definition, so let's consider some example. For example, we have some parameters. For example, like we want to we have time, right? And we can choose to divide our time in several activities, like studying, eating, sleeping, and having a rest. And so we have different times, like studying, eating, and other activities. And we want to know the best set of these times that will give us the most reward, which means that we will, for example, in your case, you want if you want to study harder and you want to get the best marks at all, then you want to maximize your marks. So you have some. This is your parameters. And if you have these parameters, then you get marks. So this is value you want to optimize. So what means optimize? You want to get maximum of it, and you want to find such parameters t1, t2, t3, and so on, that you will get the best marks, right? So that means that we can apply this example to give a definition of optimization. So basically, if we have some system, some set of parameters, and parameters, then optimization is a search for optimal set, and optimal set can be denoted as x with a star. So we have the best parameters for optimal set, which gives you maximum or sometimes minimum. It depends on, obviously, on task what you try to accomplish, which gives you the maximum or minimum value you want to optimize, value v. And because of this definition, we can see that our optimization problems can be divided in several classes. By several traits. First, we will divide them by set of parameters. So, in case of example we've talked about trying to maximize your schedule and find the best times you want to divide your day, you can actually divide your time in continuous sets of time. So that means that you can study 1 hour, or you can study 1.5 hours, or you want to study 1 hour and 11 minutes. It's up to you. You can always find any value, and any value on what you want on numerical line. So if your parameters are continuous, that means that they can be these parameters can be anywhere you want. They're just real numbers. Then this optimization problems is called continuous. So it's a pretty basic example, and continuous optimization problems are very common because in physics, in real world, we have all our values are pretty much all values are continuous, and we can choose any value you want. However, if we take, for example, game like chess, and we have a set of parameters, like, for example, position of each figure on board, and you want to change set in that way. You want to find the optimal the optimal change in positions. So you want to win in chess, and you want to know the optimal policy or strategy to win in chess. And in that case, your parameters, which are positions of board, they are discrete. So there are only like 64 possible positions, and there are maximum 32 chess pieces. That means that even if we multiply 64 by 32, we still will get we will have still some number of different options we have, but this number won't be infinite. So our set of parameters cannot have infinite options, and that means that this optimization problem is discrete. Also, we can divide them by values, because sometimes, for example, if we take chess again, then our values, and if we win or we lose, or even simpler, if we take a tic-tac-toe, you know this game, when you just have to you have to mark zeros and x's, and in that case, if you have some optimal strategy, and if you know strategy of other player, then you can predict who will win or who will lose with 100% certainty. So that means that you always know whole position, and you always know what you achieve and what you maximize for. So they just can be like not random, which means that value is always defined with 100 certainty by its parameters. And we can have random optimization problems. Or it's sometimes called stochastic optimization problems, where, for example, you play a game of with cards, and you don't know exactly position of each card in your deck, and that's why you just cannot predict who will win, and you can only say what probability of winning. You can calculate pretty much or estimate probability of winning, but you cannot calculate who will win. So these are actually different classes of optimization problems we will talk for pretty much entire course, and because discrete optimization problems which are not random are very simple, because we have only finite set of parameters, we'll start from them. And very good discrete optimization problems, which we will talk for about 3 lessons, is traveling salesman problem. So this is a toy problem we will try to solve by different optimization algorithms. And using this problem, you will understand better how this algorithm works, and you will try to implement them in other tasks. But this will be a very good example, very good starting point. So consider that you are a salesman, and you want to you are going for a journey when you will sell your product in other cities. And you start from some city A, for example, and you want to find the shortest route route. This is first. Find the shortest route. What is a route? Route looks something like that. So you are going from A to B and to C, D. And the more important, you then return to A, and the routes are these. So you try to find the shortest route, and you can be in cities, you even not can, but must be in each city only once. That means if you are currently in city D, and you are traveling then, you just cannot return to city D again. It's not allowed by rules. So your route must be complete, which means that if you are starting from city A, then you must return to your initial city A. Must return to initial city. This is three basic rules which define this problem, and now and what we have, and we know all coordinates of each city or distance from different cities. So you pretty much know distance from A to B, A to C, A to D, you know distance from D to G, every this distance, each of this distance you know, and now you need to define which route is optimal, is the most optimal, which route is the shortest. And this is discrete problem. Why is it is a discrete problem? Because our parameters are actually just names of cities which we are going to travel. For example, for this route, it can be written as A, B, C. And so because we have n cities, we will just have n parameters. For this example, we will have 7 parameters, and each parameter can be only A, B, C, D, E, F, or G. So you can create entirely new route but still each parameter has only 7 choices. So it can be A, B. That means that there are finite set of parameters, and that means that there are finite different choices and different routes. Yes, this number can be pretty good, pretty big, but at the same time it's not infinite, which means that this is still a discrete problem. So first algorithm we are talking about is brute force. This is the most probably stupid algorithm which you can use in in optimization, discrete optimization, because what it does, it just loops through each route, each possible route, and then it finds the optimal one. So brute force, for example, if we let's have smaller amount of cities, A, B, C, and it just loops through every one possible route. So it means A, B, C, A, C, B, and so on. C, A, B. Or for example, we can start from one city, and there are only 2 possible variants. ABC or going ACB. And if we are talking about, like for example, 7 different cities, then this number gets bigger and bigger. And now we will try to implement this algorithm in Python. So that's our derivative. So first of all, we are creating our data we are working on. We are defining function which will create map of these cities and print them on a map. So I created function which whose input is number of cities, and this is some arbitrary number which just defines randomness of the cities, and in that way we can control randomness. And if we have the same number 78, then we will get the same number, the same position of each city every time. So this is our map of cities, and their names are just letters of alphabet. And now we will need to find the best route, which will, for example, start from city A. So first of all, because we've defined our coordinates of each city, first of all we will need to calculate distance between each possible city, because if we are calculating it later, when we are doing brute force, then this algorithm won't be optimal and it will take more time. So we just pre-calculate all these possible combinations of distances in this distance dictionary. So we just create dictionary. And now let's print I'll see you how it works. So this is our dictionary of all possible distances between cities. So here we have a city number 0, or city number 1, or city with, whose name is A, and its distance to city number 1 or B is equal to that number, to city C is equal to that number, and so on. And we have all possible combinations, and it's done only for better time using of code. Now we are getting to important part. It's actually an algorithm which finds all possible routes which can exist in this Salesman problem. So what it does, so first of all we have some list path which is called path, and this list just defines our whole route. So let me explain. So here we have path. This is already route that we've had taken, and now we consider it for a bigger system like 5 cities, for example. So this is our route we've just completed, right? Now for each, now we check if this route is not complete. This route is not complete because path consists from only 3 cities, but we have 5. That means that our route is not complete, and that's why we then loop through every possible combination, which means that from city number C we can go to D or E. And now what this function does is actually that first it goes to A, B, C, D, right? And then we use this function again. So this function is recursively defined, which means that after we've checked this route is not complete, we are doing this function again, and we see that our route is not complete again. That means that we are going to. That means that we are. We just ended up with this route, and now we can go only to CTE. And now we use this function again and get our route. The same can be done after that. After that function have completed doing this the route, it just returns back there and starts all over again. In that case, it chose route to be A, B, C, E. And that means that and now we can go only to CTD, which it does in the next step of this function. And that means that we have such tree of decisions, and if we start from point A, then this tree will be quite big, and I just cannot write down on this blackboard. However, it means that it goes through every possible variance that exist. And so it's just must end up with all complete routes. Then we just add distance from our last city to our initial city, because by definition of this problem we will need to stop where we started. and then we append our distance of whole root and our path to special list roots, which all paths are stored. And distance is complete. It's sum between all cities, which means that it's complete distance of this particular route, which we want to optimize. And this is how it's done recursively, what I've talked about on Blackboard. And now we have this little function brute force, where we just define our list roots. Then we fill these roots with all possible combinations of paths, and then we just sort. This is the most important one. You'll need to remember that, because in your homework you will actually return to this line of code. And what this function does, it just sorts this path by its distances. That means that first element of this list will be the shortest distance, and the last one will be the longest distance. And finally we can print out this root. So now let's define this function. Define this function. And define a function which just chooses the best route and prints it on a map. So this is our list with all possible combinations of paths. This is where we create our dictionary, and this is where we use brute force and just print the optimal one on the map. It takes some time, and indeed it gets the best route. So the best route starting from points from city A is A, C, J, and as you can see. And that means if we start from other city, like city B, then that means that obviously after some calculations it will end up with the same route, but it will just start from B, and it can go like B, Y, A, C, J, and it starts over. So we will end up with the same route, with the same image, but it will just start from other city. And here I checked computer, because if you consider this particular part of map, then first when I saw it, I wanted to go like G, E, H, F, and I wanted to check if computer was right, and indeed computer was not mistaken. So this route, is the most optimal and the best. So indeed route G, E, H, F is longer than the route which is shown on this map. However, this brute force, while it gets us always to the best variant, because it just loops through every possible variant which exists, which means that we just cannot ignore some optimal and cannot throw some optimal variant. So we can write down advantages and disadvantages of these routes. So cons, which is good about this algorithm? It always finds the best route. But minuses, number of these routes can be very, very big. If we are talking about 3 cities, then number of routes can be either in this direction or in this direction. So there are 2 possible routes. If we are talking about 4 cities, then we can go like that. We can go like that. So there are actually, if you write them all down, there are actually 6 routes. If you can rotate them, there are 6 routes. And actually the formula for n cities, number of routes, is equal to n minus 1 factorial, because we can choose 1 city, then we can choose n different n minus 1, excluding the city with which we started from. We can go to n minus 1 different cities, then we can go to n minus 2 different cities, and so on. And after we've multiplied everything, we will get our factorial. And what does it mean? It means that if we are talking about n is equal to 5, then 24 routes is pretty easy to calculate. But if we are talking about n is equal to 20, and 20 minus 1 is approximately 10 into power 17. So it's already a huge number to calculate, and it would take ages, if to be exact, several thousand years to calculate through every possible route if we just have 20 cities. It's not very much. It's not very many cities, 20. And what will, if we take n is equal to 1,000 cities, then this number will be just too enormous to just comprehend. It will be huge, and obviously computer just cannot find the best route because it will take too much time. So the disadvantage of this algorithm, it takes too much time. And this is a problem of pretty much every brute force for every problem, because in most discrete problems there are, if we are increasing number of parameters, number of possible options is increasing very, very quickly. And the final algorithm we are talking about now for this lesson is greedy algorithm. It's even simpler to understand. If we have such system of cities, and we start from this one, A, we just go to the closest city, which is possible. Now we can see that there are 3 options, and this city is the closest, so we go to this one and to this one. then to this one and back. And it's very easy to understand, and it's got its name greedy because we we cannot see future, and we just go to the most optimal optimal option after only one turn. So plus of this advantages of this algorithm, it's faster. Because we are starting from this point, from this city. Now we have to calculate distances between n cities, right? n minus 1 cities. After we've moved to the closest one, we have n minus 2, n minus 1, n minus 2 options to calculate, and so on. And this number is proportional, not for big numbers, I won't calculate the exact formula, I just say that this number is proportional to n squared, approximately. That means that if we double number of cities, then number of calculations that computer needs to do will increase in 4 times. Also, but its disadvantage is that it's not optimal. It's not always optimal. The result we are going to get is not optimal in all cases. Like, take a look at so we are going to this, then to the closest. And now so we can go if we have even more numbers of cities, this is probably actually an optimal way. If we have a more number of cities, then sometimes it will, because of its greedy nature, it can trick itself and go in some knots or some not optimal ways. And actually, when we will go back to Python, you will see that sometimes it creates such loops which are obviously not optimal, and that means that this approach just cannot you get sometimes to the optimal one, and in fact sometimes it can get you even for the worst one, but it's a rare case. That's why this algorithm, because it's so fast but not all optimal, it can be used to approximate, to get approximately optimal solution, and then to start from this solution using some other algorithms we will talk about in next lecture to get the most optimal. So this algorithm can serve as a starting point for some more complex algorithms to work with, because if they start from the very beginning, where every pass is random, then it will take much more time. So this is our greedy algorithm. We will define 25 cities. So already this number is this number of cities just cannot be solved by brute force. we again we define our greedy algorithm. So because greedy algorithm doesn't get you optimal way, we usually loop also through every possible starting city. So that means that we are not starting from only one city, for example A. We can also start from city B, from city C, and see what path is the most optimal from these greedy ones. Because sometimes starting from one city can be better from another and can get you away from some loops. So and finally we create our distance dictionary, this function we've already defined, and finally we can use greedy algorithm and our printing function to view this. So as you can see, this route is pretty optimal, but not very, because of this loop, which we can see. So we started from some, so if we consider this city, then all these cities are already, you've already been there, so you just cannot go to city number G. That's why you have to go C, and then you go like that. Oh no, sorry, actually you go like that, but then you find out that number C is very distant to next city F, and you have to go so unoptimal to get to the city F. And here are your practice tasks. First task, you'll need to understand how probably greedy algorithm gets you to the most optimal example. So in this task you'll have to calculate or estimate the probability of the most optimal result in greedy algorithm, and you will see that for very small numbers of cities like 3 and 4 and 5 it will get pretty much every time, but if we take bigger and bigger cities, that our computer can generate can get into some trouble with these loops as you've seen before. So in this task you will have to do a little experiment, a little research. You will have to parallelly use not only greedy algorithm but brute force, because your brute force will check your greedy algorithm and say if this is optimal or not optimal way. There are several hints for you, and also there is task to create the longest route using brute force, and how to create longest route using greedy opposite to greedy algorithm. And probably that's it for this day, and bye bye.